Hi everyone, my name is Noor Fahmi and I'm a data scientist at #paid. I'm currently a stream owner for the Math and Foundations stream here at ACE. If you don't already know us, ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit AI.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. We currently have 14 different streams that are focused on various ML topics, and this session is in Math and Foundations. Hope you enjoy it and come back, and if you enjoy it, don't forget to smash that like button and click subscribe. So without further ado, I'd like to introduce the speaker for today, Mahdi, who is a R&D engineer at Sunnybrook Research Institute.
Hello, Noor. I'm very happy to be here at one of the ACE spotlights. So thanks for having me in this session.
We're excited to host your talk today, Mahdi.
Okay, so hello everyone. This is Mahdi Biparva. As Noor mentioned, I'm a research and R&D engineer at Sunnybrook Research Institute. So today I'm going to be talking about one of the contributions of my PhD project. So it's almost more than 6 months that I finished my PhD at York University in computer science, and there I was part of computer vision center at York University, vision center at York University, and worked with Professor John Sotsos. And the focus of my research was on visual attention and the integration into deep learning framework for different types of tasks, vision tasks that we have. So today I'm going to be giving you the open problems that we currently have in computer vision with respect to deep learning modeling approach, and provide research motivations, and then kind of get into a little bit sense of current trend of attention in deep learning. We're gonna see different paradigms of top-down processing, and then I will introduce the foundation of the kind of novel pruning approach, which is introduced as STNet, which is a top-down selection in convolutional networks, and from there we will see how pruning will naturally emerge, and then I present the formulation that kind of generates some notion of um, um, pruning in a neural network. So as we have seen all throughout the past years, neural networks have improved the performance of um, different computer vision tasks. So for instance, we know that deep learning in 2012 had the first impact on object classification, and later on we have seen advances in object detection, different sort of segmentation, such as semantic segmentation and action recognition, and then the joint modeling of language and vision in visual captioning or question answering. And recently we have seen novel ideas in order to improve the architecture of neural networks for such tasks such as ResNet, DenseNet, and STNet. One of the problems that recently have been gained attention of the community is um, the computational bottleneck that the mobile platforms have. And for that, we see that um, the high performing models are usually very computationally extensive. So if I bring on my laser pointer, so here in this figure, we see that VGG 16 and 19 are on the right top corner, which means that they have a huge amount of operations for a high total accuracy. But for a mobile platform, we definitely need to sit somewhere here, which is low operations but still high um, computation. And we see that in recent years that the shift of research is towards proposing models in this area. And here also we see that for things like VGG variants, we are sitting on the left side, which means that the actually this is the um, density, one accuracy density means that the amount of density of the accuracy over the computation. So lower means more computationally demanding, and higher means less demanding. So the other aspect of the current problems that we have is the fact that state-of-the-art approaches kind of suffer from things like adversarial attacks. So in 2015, we saw Goodfellow kind of brought this to the attention of the community that adding some sort of noise to a natural image would degrade the performance of state-of-the-art model while it's still distinguishable for a human observer. And this also has been tested on a mobile platform um, application. The other thing is that
What captions there?
what's that?
What were the captions there for the image?
This
On the
one.
yeah,
So it's the input image. It's an image from dataset, and then this is the clean image. This is the adversarial image with some noise,
yeah.
and then another noise.
What did it get
And
classified as?
so the category kind of is small, but the original one is washer with high accuracy confidence, and then it changes to some other stuff. Yeah.
Interesting.
So it shows that so this is a mobile app. It shows that in a mobile app. So if you point the app to just a typical washer, the kind of the app on the mobile can predict the correct one, but it seems that they artificially kind of inject some noise to the app, and then the performance degrades. So it's
Mhm.
just trying to show that it's robust to mobile platform too. And then we have another thing which is input noise and out of box perturbations. For instance, here we see that um, the model could actually gets fooled by some noises, that some patterns that still we can detect the sign as a stop sign, but then model performance degrades. And recently there are interesting things like adding different type of expected noise to images, and then checking the sensitivity of models. For instance, here we have things that imitate, for instance, different level of brightness, something that imitates fog, frost, snow, and these have been very interesting for the autonomous driving application. And the other thing is visual confusion or contextual interference. And that means that if we have state-of-the-art object detection and we just simply add some sort of object instances to the input image, the performance degrades such that is not kind of recoverable by any sort of post-processing. So having talked about these problems that we have, the motivation is that humans in a daily life, they are exposed to a huge amount of sensory data in a dynamic task setup, and then we very easily and with comfort benefit from the attention mechanisms that we have in order to accomplish short and long range tasks. Um, and neural nets specifically have kind of pushed to the limits on improving the performance on benchmark data sets. But networks are getting complicated, benchmarks are getting bigger, and tasks are getting compound. So in order to keep up with these requirements, kind of we have to be able to um, um, harness the capacity or computational capacity of our models.
I'm also
Uh,
very interested to find out how attention can be used in a way that isn't computationally expensive, especially on like a mobile app, like you mentioned before.
mhm, yeah. So just to elaborate on that more, a vision system actually to keep up with human level of performance needs to be successful on a multi-domain, multitask settings, and deal with large amount of data in a dynamical environment. And the human motivation from human vision system is that um, attention as a selection and gating mechanism can help us to deal with
For that,
these. Okay, so I probably will get to that a little bit more.
so
Um, And what we have, oh, like another thing that we are that we learn from human visual processing is that we in humans we have not only bottom up stream of visual processing but also top down stream, and this has been recently um, um, got into the kind of deep learning and neural network framework. So with this in mind, let's see what attention has for us. So obviously it's very common in biological studies from psychophysical side all the way to the neurobiological side. So it's very well known in that community, and this is very interesting to see that since that deep learning is some sort of ins inspiration from the human processing routine system. Actually, it's nice to see that how attention could fit into that. So, what we mean by attention is that we actually, from our childhood ages all the way to the um, um, old ages, actually we learn that in order to solve the problems and kind of accomplish daily tasks, we need to be able to attend to different modalities at any time. So humans have different sensing modalities, and we have task definitions in our mind, so then we can define routines that benefits from attention in order to decide what to process, what not to process, and this dynamical um, 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 processing kind of is some notion has intrinsically has some notion of attention in it, and very two very well defined actually modes of attention is covert attention and overt attention. Then for covert attention, actually in vision particularly, we talk about so the overt attention, let's begin with that. Overt attention is what we commonly do at every second. So the eye movement is what help us to select from our environment what to look at, what to um, um, see, and what to collect information from. And the other one is covert attention.
Mhm.
In covert attention, actually, we if we keep our eyes fixed at some point, we still have this capacity to shift the point that we select and process information from. So we actually have some field of view that we can perceive our surrounding. Once we fix our eye at some point, within that field of view, we still have some attention mechanisms that help us to pay attention to different points of the um, field of view. So that these are two kind of um, different modes, and what comes into so the work that I have done in my PhD was studying covert attention in neural networks. So we know that uh, a, a, a deep network is basically a fixed um, representation on a given image, and we want to see that how we can kind of develop some attention mechanisms on top of this representation in order to kind of localize or select processing um, over the network. So very quickly, just give you a very overview of the current attention um, modeling in deep learning. So it has been within the few years has been very popular and widespread in different domains and tasks. So ranging from object localization detection all the way to network belief visualization, generative models, natural language modeling, and even for eye movement modeling in robotics application. Actually, we can roughly categorize approaches in two different paradigms. So one is those that use parameters to come up with some notion of kind of attention maps, and the others have non-parametric um, um, approaches. So in the parametric ones, we just typically it's a neural a typical neural layers that we are familiar with, and it's usually involved in an end-to-end learning um,
Yep.
approach, and requires fine tuning. And for instance, we have self attention and LSTM forget cells, that sort of thing. But on the other hand, non-parametric approaches, they don't need fine tuning. They relies on some pre-trained networks. They're quite fast, and we have a number of them listed.
So
So we
the audience
can,
may not know this, but you were actually a co-author for STNet as well.
which one?
You were actually a co-author for STNet as well, which is
So that's gonna be the foundation I'm gonna get into very shortly. Yeah, that was the work, actually the beginning, the first work that we introduced, the kind of framework that we can have top-down attention integrated into neural nets. But here we have just very quickly how we kind of see parametric approaches. So as you can see, we usually have some sort of layers that kind of generate some attention maps based on which selection happens, and then we aggregate features and then send it to the next stages. So they kind of have very common um, aspects, and they usually need to be learned during the learning phase. But on the other hand, the non-parametric based on some rule-based definitions and some heuristics that kind of is defined on top of the neural network, and then kind of introduces these attention definitions um, for us.
And how do you find those heuristics or those rules? Is that
Mm,
dependent on the context? Is that decision based from the engineer? Is it latent?
so for the non-parametric approaches, you mean?
Yeah.
So for non-parametric approaches, basically they are based on some sort of domain kind of knowledge representation. So for instance, in our work, we are inspired by some studies in cognitive science, and then we kind of use those aspects in order to define what uh, happens at each layer, and then gradually we see that it evolves such that we have this notion of um, attention. There are other things that use different sort of um, mm, approaches, but the thing is that the common aspect is that they don't have any learnable parameters in
Mhm.
order to get the attention from. So they kind of just you add them to the network, and then using the pre-trained network, you kind of get that sense of attention.
Yeah. It's interesting that you base those decisions off of what's happening in cognitive science.
Yeah, so that's kind of the inspiration that we study what humans benefits from, and then we kind of it's actually in a similar fashion that neural network and all these pieces in deep learning have been kind of started from. It's usually nature is a good inspiration for AI research, I would say.
Oh,
So here I just very quickly categorize their aspects. So in the bottom-up approach, so actually we have it's another thing that it's interesting to pay attention to is that we have a bottom-up attention approaches and top-down attention. So bottom-up approaches they're very common, and most of the things that we have, such as self-attention, all these sort of attention understanding we have in deep learning are based on bottom-up feed-forward pass of information into the neural network. So all the for instance, self-attention, LSTM. So by that, we mean that attention maps kind of are derived from the information that is generated from the early layers all the way to the top. So in on the other hand, in the top-down approaches, we benefit from both bottom-up and top-down, and this is kind of going to be the novel approach that STNet kind of introduced in a few years ago. Um,
is the top-down approach to the way that humans typically think about?
yeah, so that's more or less what humans benefits from. So in humans, regardless of what we think of in deep learning, which is everything happens in bottom up, but and the top down is very weak. Just it happens in the learning phase. But in human, at any time, not only learning but also um, perceiving and doing inference, any sort of things, we still have a strong flow of information from the top of our visual system all the way to the intermediate and even early. So there are widespread evidence in neuroscience and cognitive science that these are um, not negligible, and kind of at some point we will see that sort of computation in deep learning hopefully soon. So I'm gonna speed up a little bit. So for okay, so here I just very quickly say that top-down processing, as I just talked about. So, for instance, in order to calculate gradients, we have a backpropagation algorithm that is kind of again some sort of top-down processing, because the top of the network is the semantic layer, which is the label that we have, and then we use the prediction and the ground truth in order to kind of um, determine how much we are off, and then we use mathematics to kind of back propagate that amount all the way to the early layers, and then we use that to update the parameters. But and also we have that some sort for semantic segmentation, but it's just not very strong. But for
So is,
weekly
yeah. Oh, sorry, finish your point.
for a weekly supervised task, which is interesting to look at, and I will show that in a moment. We kind of use this top-down processing in order to localize the region of confidence of a network throughout different layers. And then we use that in order to mark that region as the salient region that the object of interest is in. So I'm going to get into that in a moment. So what was you were asking?
All of these variants, they're all based off of the workflow of a feed-forward network. Am I perceiving that correctly?
Yeah, that's correct.
Awesome.
So just as we all know, a bottom-up convolutional network, we have parametric layers, multiple parametric layers, convolutional activation function layers, normalization, different sort of pooling. And what the goal is that given some input image, which is here, for instance, a bicycle, we want to predict the label. If it's a classification, if it's detection, we want to predict not only the label but also the bounding box. And if it's semantic segmentation, we also want to predict the foreground mask. So I kind of studied four main questions in my research. So the first one is that given such network, how do we know the important features that contributed most in the prediction of a target? And then we want to study how the selection can be done in a neural network, and then also how does the top-down processing can mechanism can help us to do that. And then the second question is, so now that we have a mechanism to select features, what are they good for? Can we use them in a multi-domain or multi-task setting, and then um, use them to improve the performance? So that's what I used in a semantic segmentation setting, which is not what I'm going to talk about today. But and this third question is, can we use this selection mechanism to also select over the parameter space? So having a number of kernel filters, can we select those that are important? And lastly, I studied how we can use this selection mechanism for the representation learning and kind of gain some level of higher degree of robustness to things like adversarial attacks or out-of-box perturbations. So these question one and three are the main um, focus of today's presentation. So kind of the computational foundation is that we have some input image, we have the task predictions at the output. The model is a multi-layer network. Parameters are optimized using some algorithm like backpropagation here. And then um, we have label prediction at the top. So bottom-up processing is just what we talked about, and top-down processing is that given some task signal like the labels, we want to see that what part of the network contributed most. Actually, I talked about that. So very quickly, I just want to give you some a better sense of this bottom-up, top-down processing in a toy example. So let's assume that we have a three-layer neural network, which is convolutional, but in a 1D dimension. And these are the connectivities that we have. And as you can see, it's a convolutional network. And the last layer is kind of some sort of fully connected. So we feed it with some input X, and then the information is processed as the arrows show. So it's going from the bottom all the way to the top, and we aggregate information at each layer. So then we have the hidden activities at layer 1, 2, and 3, and then here we predict class labels. Um, so information is encoded at each layer, and spatial information is gradually reduced. As you can see here, we have larger resolution, and here the resolution is decreased.
And
Uh, on the other hand, semantic information kind of increased, and at the last we have fully connected layer and the class label prediction. Now the question is, where is what contributed most to the final prediction? So I want to know that for predicting some class C2, I want to know that, for instance, sorry, I want to know, for instance, at this layer, what contributed most to the prediction of C2. And this is where we propose to do it in a top to down um,
yeah,
fashion. And then here we see that if we have a regular neural network, given some image of panda, we have processing all the way to the end, such that here the label is predicted. And then what we do here, we have a similar structure that is kind of defines the top-down structure. And then what we do, we signal the top of we signal the label, the panda label on, and then the kind of top-down network kind of select for us the regions that are most important. And then what we do at some layer, we say, okay, these are the regions that are kind of highlighting the salient regions for the panda, and then we propose the bounding box. So this comes under um, the, the task of weakly supervised object localization.
so I have two questions. The first one is, let's just go over geometrically what happens to our input data. So here we see after we take the very first layer of the image, it starts to become more and more condensed in
Mhm,
bottom-up processing.
mhm.
That's fine. That's another CNN workflow that I've seen enough times to be familiar with. But then what happens with the top-down processing? Does it get restretched back into its regular image form?
So one thing that I need to highlight is that actually the bottom-up processing is a regular deep learning network. So here we have learnable parameters that are kind of fine-tuned and kind of optimized for instance, classification task. But the top-down network is basically doesn't have any learnable parameters. So all these connections and these activities throughout different layers, they are basically calculated and determined on the fly based on some rules and definitions that we kind of borrowed from biology. So the thing is that we don't have any learning parameters, and the notion of non-parametric top-down attention kind of emerges since we don't have learnable parameters and everything is kind of computed on the fly. So for instance, the region that highlights panda is totally different from the region that highlights, for instance, bicycle or a car or different categories. And they, as we will see, they rely on a number of inputs, a number of kind of processing stages that doesn't need to be optimized for this. They're just kind of rule-based approaches that are
Yeah.
they're kind of simple but effective. So that's what we are gonna see.
So just to confirm, there's no deconvolution happening in top-down.
No, so no, the
It's just a
convolution there is
holistic
no.
approach that you mentioned before. Okay,
Yeah.
cool.
For the top-down part, as we just talked, we have actually three stages of computation at each layer. The notion of non-parametric processing, and then here we define the units at each top-down layer as gating activities. So they're kind of determined on the fly. So we begin from, as I mentioned, some class hypothesis. So for instance, here we are looking at the hypothesis that represents panda. So then we go layer by layer down. The information is kind of routed through the selected kind of connections, and then we kind of gradually go all the way to the early layers at some point that we stop. Um, Go ahead.
Yeah, what do you mean by gating nodes? Is it like a logic gate?
So the gating idea is that basically information is gated. So the top-down information flow is gated using those. So they're like kind of you can consider them as some um, kind of kind of processing units that have values from 0 to 1, for instance. And they kind of determine in at each layer. So we have the kind of the tensor of gating activities. So at each layer, they kind of get positive as we do the selection. So the selection kind of um, sets the value of the gating unit. So I kind of get this. This is gonna get more clear soon.
Okay.
Don't worry. So one thing is the top-down selection is sparse, and then we will see that. So then the so gating activities at early layers kind of collectively highlight the region. So let's get back to the toy example. So here, this is the top bottom-up network. This is the top-down that in the size and number of units at each layer is similar to the bottom-up. But we have this, so these are getting um, activities at all different three layers. So what happens here, we set the signal, which is attention signal for some category. Here we set it based on the prediction, and then selection, as you can see here, selection kind of receives the input from the bottom up layer. So we have the input here, for instance, fed into the selection mechanism, and the selection mechanism determines which one of the connections here should be active. Once they are determined, we use the top node, which is the top gating node, in order to propagate to the bottom layer and set the values of these two gating nodes in the layer below. And we continue doing these selection processes for different number of layers, and such that at the end we get to the input layer, and then we say, okay, these are collectively selected by the top-down mechanism, and they kind of introduce some notion of attention that we have in humans processing routines, and then we say, okay, the input of G2 and G3 are the most contributing to the prediction of the class hypothesis 2, class 2. So we have a number of things that kind of add extra details. For the sake of time, I'm gonna skip. So something to mention is that so selection, as you saw, happens within the receptive field. So and let me see. Yeah, and the input is the hidden activities of the bottom-up network and also the weights into this attention process unit, and then it determines the connections. We have developed CUDA kernels for this in order to speed up the processing. One thing interesting to mention is the output-centric and input-centric paradigms in the bottom-up and top-down. So the bottom-up is output-centric, which means that the input are aggregated for one particular output. But here in the top-down, the output kind of um, what do we say? The output kind of is diffused or spread into a number of output units. So here we have these three stages of selection. So again, we have feed-forward bottom-up processing on the top and top-down selection on the bottom. So this is just a regular convolution operation that is in addition with the ReLU non-linearity. And in the top, we just show that at this stage, once we multiplied weight and the input hidden activities, we kind of feed it into the top-down processing at three different stages in order to do the selection. This is just just showing that the element-wise multiplication happens at each layer. Mm, So very quickly, we say that the reason behind these three stages is that stage one is kind of tries to reduce some noise interference within the receptive field. Stage two kind of does some sort of grouping based on spatial contiguity, which is again coming from the biology side of the study. And then the stage three kind of propagates the normalized gating activity to the layer below. And for that, we design custom PyTorch layers in order to make it end-to-end with PyTorch. So the good thing is that the memory and all the layers um, very in a straightforward manner kind of integrate into any typical convolutional networks in PyTorch, and then we can benefit from things like gradient routing within the neural network, um, which is part of a necessary part of the research in not this work, but the other contributions I had. And for weakly supervised object localization, again, I apply it to ImageNet. So here, for instance, we have, so this is the case that it's object localization, object classification, and localization. So every time we have one instance of the object in the image, it's not multiple instances such as those we have in object detection. So what the goal is that given this, for instance, input image, we want to not only predict label, but also kind of predict the region that the object is. There are a number of different previous approaches that are mostly based on um, non-parametric attention selection mechanism. And then we show that the performance is indeed comparable with the state of the art and kind of is effective um, performance wise. We have here a number of samples that we predicted the regions for. So the top ones are the successful, bottom ones are the failed ones, and mostly the failed ones are due to the fact that we have multiple instances. So for instance, here we have multiple instances, and the network kind of failed to localize, or there are interesting things that uh, kind of triggered some research work later on, which is kind of the contextual interference. So, for instance, in ImageNet, there's no person category defined for the network, so the network kind of um, tied kind of the representation of a face with this stick on the face, so kind of couldn't distinguish between them. So it's widespread. For instance, here we have this instrument, but the network couldn't localize it properly and assume that it's just a person.
That's interesting that there was a consistent pattern with the failed cases.
Mhm. Exactly.
Yeah.
And then here we have some visualization in order to show that, for instance, for the dog face, so it could visual kind of highlight the region. So the top one is using VGG and bottom one is using GoogleNet. At that time, they were kind of trendy. And I have some ablation studies to show that if I remove one of the stages of selection, what happens. So for instance, here I remove stage 2 and we show that the selection performance kind of degrades. And here again, we show that this idea of contextual interference, that the correlated accompanying objects kind of has a significant role in the prediction of some categories that have been seen mostly with that one. So here, for instance, face or airplane and wing kind of couldn't be distinguished properly. Uh, so this is just what I wanted to give as the base of the pruning idea. So in the pruning idea, I'm going to get into that. So the idea in pruning is that, so generally for mobile platforms we always want to have some compact representation. So the idea is that neural nets are overly parameterized models, and if and we can kind of squeeze the model size into a smaller one such that the performance doesn't degrade, and then we can benefit from the accuracy on a mobile platform, because we have obviously resource limitations on mobile platforms, and we want to have models that are kind of in a few magnitude smaller in terms of size. So there are very popular approaches that are have been devised in the community. There are some that do weight clustering, similar to clustering problems that we have, using things like k-means or different variants. There's another one that does low rank approximation. For instance, the familiar one is for PCA, that using PCA we can reduce the dimensionality of some tensor. So the idea is that we, given the kernel filters, can we use things similar to PCA that comes under low rank approximation to lower the size of the kernel filters, so then the kind of the processing could be faster and less computationally demanding. The category that we are falling under is this weight or connection pruning. So these approaches use some sort of importance to determine though the weights that are mostly contributing to the representation. to the learn representation, and then use those connection those elements in the filter to kind of um, rely on and then use for the inference phase. And there are some sparsity imposed approaches via regularization. Um, so in our selective approach, so the idea is that as we saw, we have this top-down mechanism that what we saw is the selection over the hidden activities or hidden tensor. But on the other side, we can also use this selection mechanism to come up with some sort of importance maps, and then use them for the for pruning and selecting the proper part of the kernel filters. The nice thing about our approach is that our approach is class specific, um, while the other approaches are class agnostic. So the the fact that we always use some top level attention signal at the semantic level in order to originate the kind of top down selection from is the nice part that kind of help us to get to a kind of um, uh, stronger pruning result.
That's also
So go ahead.
um, yeah, I'm glad you just pulled up this diagram because I was about to confirm that the workflow there is benefited from the workflow here where you get the class label and then that's fed into the attentive signal and then it goes down your top-down layer. That's really cool that it can do that.
Right, yeah. So that's the interesting part of the work, that this kind of pruning idea kind of emerges naturally in this top-down framework. So here, let's get back to this figure that at each stage, the selection kind of determines the connections or that are important. So that's here we need to differentiate between connections and kernel filter weights, because kernel filters basically are they kind of determine the connections, but they are not always the same. But the good thing is that we always benefit from this connection selection for each particular node. So we always say that it's not enough to look at the kernel filter in order to come up with some pruning mechanism, but also we need to consider it at every single time that we apply it to the network at that layer. So here we see that for one particular node, for instance, these weights, these connections are selected. So what we do, we pull them into some persistent buffer, using which we accumulate these kind of importance values, and then we trigger the pruning schedule, and the pruning scheduler trigger them in order to determine the mask using which we prune the bottom-up network. So we do it for all the layers, for all the nodes that are kind of activated throughout the top-down network. And once they are accumulated into persistent buffers, what the pruning scheduler does is for a number of times, a few number of times, like 5 times, 3 times, 6 times, so depending on the validation result, we what we do, we kind of update the masks that we have at each layer, and these masks basically prune the kernel filters of the top down of the bottom up feed forward neural network. And once the pruning has been done, we do some fine tuning in order to kind of boost the performance, and we repeat this for a number of epochs, number of times, in order to kind of keep the performance at the competitive level with the baseline, and then we stop. And then we calculate the ratio, the compression ratio, and then we see how good we are um, with respect to the baseline. So a little bit more details here. This is just a different view of the approach, that here we have this bottom-up and top-down network. The selection we have here, and then we have these weights that are basically these weights here. We add them using using additive modulation. We add them to the persistent buffer, and then the scheduler kind of has some gating mechanism that activates the update of the mask using this criterion. So we say that if the kind of um, values in the persistent buffer is above the mean plus some standard deviation, we set the mask tensor to 0, otherwise we set them to 1, and then this determines how much we want to do the how many uh, values of the weights we want to prune, which affects kind of the level of compression. And we apply it to MNIST and C410. They are very popular in this task, and we observe that the parameters for some comparable level of performance is kind of significant. So it's 58 times more compressed here, over 100 times more compressed on MNIST, and for C410 we also have some good level of compression, and the performance didn't degrade very significantly, so it's always negligible. And then we compare it to similar approaches, um, and we see that the level of compression kind of supersedes the two of the state of the art, but kind of fall behind one of them. And the reason is that that one uses second order approximation, which is kind of computationally extensive but provides stronger information for the proper pruning. And at the end, I would like to conclude the talk by summarizing what I just told you about. So I gave you a very good overview over the top-down approaches, different um, approaches for top-down processing. We saw how we can integrate bottom-up and top-down for object localization, for network compression, and then we saw how attention nowadays is kind of used in the literature, and then I showed you some understanding of top-down selection inspired from human perception, and we see that it's not always important that we have very fancy and complicated mechanisms in order to achieve high level of performance for different tasks. We can also get inspired from the nature, how we humans do daily routines, and then kind of add them to this processing machinery that we nowadays have in using based on deep learning, and then gain some good level of performance and robustness. So thank you for listening to me, and I would be happy to answer questions.
Great. So we are running out of time, but I will allocate the next 5 minutes to question taking. The first one is from Serena. And if you could go back to your first slides where you're talking about computational complexity, were you just talking about like big O notation or a more empirical approach?
By any chance, do you know the number?
No, but when you were comparing the different models
Oh,
in
okay.
terms of their, yeah, yeah. So we don't actually need to go back to the slide, but
Yeah, go ahead.
you
Here,
mentioned,
this one
oh no,
for
before that as well. A couple more.
here.
Uh, so the slide after that.
Actually, that's the beginning.
So the slide.
What was the question is asking?
When you were talking about computational complexity at the very beginning,
Oh, the
yeah,
computational here, this one?
yeah.
Okay.
Were you referring to big O notation or to a more empirical approach?
Oh, I see. I think it's just empirical. They just simply calculate the number of operations. So here is I think giga G operations is giga operations. Yeah.
Cool. I think that answers that question. Another question that I have is, um, when does the pruning happen? Does it also occur in the top-down network as well?
So
And
the pruning uses top-down network in order to calculate, compute the kind of the base of the pruning that is applied to the bottom-up network.
okay, that makes
Yeah.
sense. And then based on what connections are selected to be active in the top-down network, that are the same connections that are chosen to be active in the bottom-up connections as well. Am I
Mhm.
correct in saying that? Okay, cool.
Yeah. So every time, so if you remember, I mentioned that we have a number of times that update the mask. So every time the mask updates, the weights here changes. So we have some notion of kind of dynamic. It's a dynamic trend. So at the first time that we prune, a number remains and others are set to zero. We what we do, we continue using that state of the network and then do the top-down selection, updates the buffers, and then once the buffers updated for the second time, we prune um, actually a subset of the remained active connections. Yeah.
Mhm. Is there ever a situation where you would reprune the original network? Oh, no.
Pardon me, we would.
Is there ever a situation where you would reprune the original network only to find that perhaps you changed the original set of pruned active connections?
Um, so the thing is, we didn't study the kind of the dynamics of networks getting pruned and not pruned. So if that is the question that is um, asking about, we currently don't know which portion of, because it's a huge number of weights that is kind of processed at each layer. So we don't yet know which subset is pruned, which subset is not pruned. But the thing is that the number of pruning, um, um, actually the amount of pruning kind of increases. So what we do in the experimentation, we determine the number. It's usually um, below 10. So we have sometimes 3 depending on the task. So if for like for instance MNIST, which is less demanding, we have higher compression ratio. So for that we could go for a larger number of pruning. But the thing is, if we pass that level, what happens is that there is a point that that all of the kind of pruning mechanisms report on, and that's the point that the network breaks. So it's as if that it's um, uh, kind of is dead. So the network doesn't have any chance to revive and kind of start to keep up with the performance. So before getting to that point, we stop the pruning. But the thing is that the amount of pruning over time, over this number of iterations, increases. So at the beginning, for instance, the ratio is 10, and then as soon as we continue, it becomes 20, and then 40, 50, and then let's say
Yeah.
we stop at 50 something.
So you'll
So
never revive an inactive connection. You'll always be continually pruning on the same um, active connections.
yeah,
Okay, got it.
yeah.
We have one more question from Matten Cohen, and he's asking, how do you think attention can be used in order to find key points in images?
Key points.
Yeah.
Um, so as I mentioned, there are it's kind of attention, specifically self-attention, has been used in many different ideas, novel ideas in recent years for particularly in weekly supervised tasks. So we have different variants of weekly supervised tasks, such as the one that I mentioned, object localization. We have weakly supervised object detection. We have weakly supervised semantic segmentation. So the no, core idea of weekly supervised task is that given some label information, we want to add extra capabilities to the network. And for that, they usually need some notion of attention in order to be able to select part of the network that is important and then feed it into the subsequent stages in order to do the higher order predictions, for instance, segmentation or detection. So that's one part that is people are actively using some notion of attention, and there's also another part in multimodal information processing. So, for instance, there are cases, as I remember, I mentioned image captioning, visual question answering, that sort of thing. We have so these work on the part that we have a joint processing of language and vision. So these parts, they usually use again some sort of attention mechanisms that helps the vision system to be kind of selected and then fed into the language model for the follow-up task that we have. For instance, the visual question answering, we always want to answer some questions, and it's been shown in the literature that selection using attention can kind of help the networks to better um, be able to predict the answer of the question, and then people usually visualize to show that indeed the end-to-end network could learn to highlight the salient regions and that sort of thing. So this is for vision, which is the domain that I'm working on, but we have other sort of attention in the deep learning literature that emerges in concept works like transformers, different variants of transformers, and that sort of thing. And that is also interesting. But yeah,
Cool. So that is all the questions. I want to thank you, Mahdi, for having your talk today. And I want to thank you guys, the audience, for joining us as well. And if you would like to see more free content like this, Don't forget to visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. And if you like this video, don't forget to give it a like and a comment if possible. And with that, have a lovely day. Bye, guys. And then we wait for Xiang to, there we go. And now we're done.